Every image of the solar system you have ever seen is lying to you. Not out of malice, but because the real thing will not fit on a page. The posters in classrooms and the animated diagrams in documentaries all quietly cheat. They make the planets big, close together, almost shoulder to shoulder. In reality, our solar system is a dark arena where tiny worlds drift through almost pure nothing. Tonight we are going to tear up that rigged map and rebuild your sense of distance from scratch. If you enjoy this kind of space deep dive, tap like and subscribe so you can travel the rest of this journey with us. Think about the picture your brain probably carries around right now. 8 planets in a tidy row, maybe a cartoon asteroid belt between Mars and Jupiter, maybe even some cute comets sweeping in on thin white arcs. The central star looks modest, not much bigger than Jupiter, and everything fits comfortably inside a poster or a classroom wall. It feels organized, comprehensible, like a well-designed model that just happens to be floating in space. Those pictures are helpful for one job. They show you what exists. They let you see that there are inner rocky worlds, outer giant planets, an asteroid belt, and maybe some distant icy bodies. The problem starts when your brain quietly promotes that picture from symbol to reality. Without noticing, you start to believe that the planets really do sit there like beads on a string, a few neat steps apart, each one looming large in its orbit. If that were true, the night sky would look utterly different. Stand on Earth, in that imaginary system, and neighbouring planets would not be tiny points of light. They would be swollen disks dominating the sky, hanging huge and bright, casting shadows. Gravitational tugs between worlds would be fierce. Orbits would be unstable. Collisions would be common. In a solar system built like a poster, the story would be chaos. But when you actually look up, that's not what you see. Even Venus, our brightest planetary neighbour, is just a sharp point of light to the naked eye. Jupiter, a world large enough to hold more than 1,000 Earths inside it, looks like a star that happens to shine a bit more steadily. The reason is simple and brutal. Compared to the distances between them, the planets are unimaginably small. So here is the central idea that will haunt this entire journey. The solar system is not a busy clockwork stuffed with planets. It is mostly empty space in which a few small objects happen to drift. The emptiness is not a side detail. It is the main feature. Everything else, all the beautiful worlds and rings and moons, are decorations sprinkled through that emptiness. Our normal diagrams hide this by doing 2 cheats at once, though. They shrink the star far too much and they drag the planets far too close. To feel just how extreme the real spacing is, we need to strip everything down to one simple model. Imagine you are standing on a football field with a single object in your hands. You set a basketball down at the centre line. That ball is our star. It has been shrunk from more than 1,300,000 kilometres wide to something you can palm with one hand. Nothing else is in the stadium yet. Just you and the glowing orange ball that everything else must revolve around. Now the question, where do you put Earth? Most people instinctively keep it nearby, somewhere in the same room, somewhere within easy talking distance. Maybe they place it a few steps away from the basketball and imagine a neat ring of other worlds just beyond. It feels natural to keep the family close. That is the textbook illusion whispering in the back of your mind. The real answer is so extreme that it almost sounds like a joke. In this scale model, Earth is not another basketball or even a ping-pong ball. It is a tiny bead about 2 millimeters across, something like a grain of pepper, and you cannot place it at your feet. You have to walk. You leave the basketball at the center of the field, turn and step off distance after distance until you're about 26 meters away, around 85 feet, roughly the length of 2 full-size school buses parked end to end. Only there do you set down the tiny Earth. Now pause and look around in your mind. Between the basketball star and that pinhead Earth, there is nothing. No other planets, no moons, just empty field, empty air, empty space. If you could float above this model and look down, you would see one big orange ball and far away, an almost invisible dot. Everything between them is pure gap. That gap is what your classroom poster quietly erased. And we are still hugging close to home. In this same model, Neptune, the most distant major planet, would not fit inside the stadium at all. To place it correctly, you would have to walk nearly 900 meters away from the basketball, almost 3,000 feet, more than half a mile. You begin on the football field, stroll past the parking lot, cross a few city blocks, maybe pass a row of houses or small shops, and somewhere out there, well beyond where the crowd is sitting, you finally put down another tiny bead. That is Neptune. that is still inside the orbit of what we call our local neighbourhood. Imagine trying to build that on paper. You could draw the basketball-sized star at one corner of a poster. But by the time you mark the correct distance for Earth, you would be off the page, out of the room, and down the hall. Neptune would sit in another building entirely. To keep everything visible, artists are forced to lie. They either show the sizes correctly and squash the distances, or show the distances more honestly and make the planets so small you would barely see them. You can never have both truthfully at once on a normal page. This is why our mental map is so fragile. Our brains grab the picture that fits on the wall because it is simple and satisfying, and quietly forget that it was never meant to be literal. We feel like we live in a crowded system, a place where everything is reasonably close together. Yet once you run through that basketball model, your own planet starts to feel like a lonely boat on a huge black ocean with its nearest big neighbours so far away they almost vanish. And here is the twist that will keep paying off. This is not some abstract curiosity that only matters in a physics classroom. The true scale of size versus distance explains why the night sky looks the way it does, why space travel is slow, why the asteroid belt is not a constant obstacle course, and why even light takes minutes and hours to move between worlds. It reveals why our star dominates everything, not just in brightness, but in mass and in control. So as we continue this journey, keep that mental stadium with you. A basketball star, a pepper grain Earth, a half-mile to Neptune, and almost nothing in between. In the next stretch, we will zoom in on that tiny bead we call home, and on the small grey companion travelling beside it, to see how even our own backyard is mostly made of empty space. In that stadium-sized model from before, Earth was a tiny bead lost in a huge stretch of empty field. From up there it looks fragile. From down here it feels gigantic. That tension is exactly where we start. Before we talk about cosmic nothingness, we need to remember what it actually feels like to live on the bead. Because to a creature a few meters tall, Earth is absurdly huge. Oceans stretch beyond the horizon. Continents take hours to fly over and months to cross on foot. You can spend your entire life exploring and never run out of places. Measured the boring way with numbers, Earth is about 12,742 kilometers across at the equator, wrap a belt around the planet, and its circumference is just over 40,000 kilometers. If you could walk 8 hours a day at a steady hiking pace, it would take you more than a year to circle the planet once. If you somehow drove non-stop at highway speed, never needing sleep, fuel or rest, you would still be behind the wheel for roughly 2 weeks. From our perspective on the ground, that is enormous. An overnight flight feels long. A 12-hour haul across an ocean makes the world feel big and unwieldy. When you look across a mountain range or sail across an open sea, the curvature of Earth is invisible. It feels like the planet just keeps going. Every direction you travel opens into more land, more water, more sky. Now mentally zoom out. Take the skyscrapers and mountains and airline routes and crush them into a single smooth marble. What was once a world of oceans and cities becomes a simple sphere. No deserts, no forests, just a ball. At that point, Earth stops feeling like the universe and becomes just one object you can hold in your hand. All the drama of human history is smeared across a surface thinner than the peel of an apple. In the earlier scaling exercise, we compared Earth to the star it travels around. If Earth is a grape, our star becomes a glowing sphere about 2.5 meters across, roughly human height and a bit more, a sphere taller than you, radiating in every direction. To put that grape at the correct distance from the glowing sphere, you had to walk the length of 2 school buses. Already Earth is a tiny detail in a much bigger picture. But our planet is not alone. It has a companion, a grey cratered world that people once thought was a smooth glowing disk, then a mythic realm, and eventually a destination. The Moon is the closest large object to Earth in the entire universe. It orbits us at an average distance of about 384,400 kilometers. That number is so big that it does not land in your intuition at all. So we need to attack it from multiple angles. Start with light. Light is the fastest thing in the universe, racing through space at about 300,000 kilometers per second. When you look at the Moon, the light hitting your eyes left its surface roughly 1.3 seconds ago. There is a noticeable delay between what is happening there and what you see here, at least noticeable to physics. If you could stand on the Moon with a giant mirror, flash a bright light, and have someone on Earth watch carefully, your signal would be almost 3 seconds late for the round trip. Humans who went there took a lot longer. The Apollo astronauts spent about 3 days crossing that gap in the late 1960s and early 1970s. Imagine climbing into a small capsule, igniting a tower of fuel, and riding a controlled explosion for minutes, only to drift for days through darkness toward a grey circle that barely grows in the window. Even our fastest robotic traveller, the New Horizons spacecraft that blitzed past Pluto, would still need around 8 hours to go from Earth to the Moon. On maps, the Earth and Moon are usually drawn almost touching. A big blue circle, a smaller grey one, with a tiny gap. In reality, if you draw Earth as a sphere the size of a coin, the Moon would be another, smaller coin sitting around 30 coins away. If you held a globe in one hand and tried to place a model moon at the correct distance with the other, your arm would probably not reach far enough. You would need to walk a bit. The space between the two is much larger than most of us imagine. Here comes one of the most deliciously uncomfortable facts in the entire story. If you took all the other major planets of the solar system and lined them up side by side, they would just barely fit into the space between Earth and the Moon. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune all in a row. Their combined widths add up to roughly 390,000 kilometers. The average gap between Earth and the Moon is about 384,000 kilometers. The pack of worlds would squeeze into that corridor with only a little room to spare. Let that sink in. Every other planet you know could be tucked between us and our own satellite. All the rings and storms and methane seas on Titan, all the swirling clouds of Jupiter and bands of Saturn, all the icy depths of Neptune, all comfortably fitting in what we tend to think of as our immediate backyard. That is how roomy that gap is. And right now, in real life, there is only one thing in there: the Moon. The rest of the corridor is essentially empty. If you were somehow able to freeze time and teleport into the space between the two worlds without a spaceship, there would be nothing to stand on. No dust clouds thick enough to see, no scattered rubble to dodge. You would simply find yourself falling along a gentle curve defined by gravity, with Earth on one side, the Moon on the other, and blackness all around. The nearest solid surface would be hundreds of thousands of kilometers away in either direction. Even our technological clutter barely touches that void. Most satellites travel in orbits that are tiny compared to the Earth-Moon distance. The International Space Station circles only a few hundred kilometers above Earth. Navigation satellites sit tens of thousands of kilometers out. These orbits are practically pressed against the planet's skin when you compare them to the full distance to the Moon. In a diagram that shows Earth and Moon at the correct scale, you would not even see those satellites. They would hug the blue sphere too closely. So within the smallest stable neighborhood we have, the place where Earth's gravity wins over the Sun's for one more companion, the dominant feature again is nothing. Vast, clean, gravitationally controlled emptiness. Our home world and its moon are like two ships on an ocean, separated by a stretch of water wide enough to hide an entire fleet of other planets. We call them close because in the language of stars this really is close, but in human terms it is as far gets. As we move outward from this tiny paired system, that ratio keeps getting worse. Planets grow larger, but the spaces between their orbits explode faster. The lesson of the Earth-Moon gap is a warning. If our nearest neighbour floats across a gulf wide enough to park every other planet, what does that say about the rest of the solar system? In the next part, we will start stepping outward through the inner planets and watch our mental sense of closeness collapse even further. Leaving the Earth-Moon pair, it is tempting to imagine that the next few worlds out there are just a short hop away. After all, when you see the inner planets on a poster, they are drawn like neighbours in the same apartment hallway. Mercury, Venus, Earth, Mars, all snuggled close around the same star. At first glance, these four look like a matching set. Small, rocky, solid surfaces, close to the Sun. If any part of the solar system should feel compact and understandable, it is this one. That feeling is exactly what we are about to break. To make sense of distances here, astronomers use a special yardstick called an astronomical unit. One astronomical unit is simply the average distance from Earth to the Sun, about 150 million kilometers. It is our home base measurement, the number one on the cosmic ruler. Instead of saying a planet is so many hundreds of millions of kilometers away, we can say it is 0.4 or 1.5 astronomical units from the Sun, and immediately see how it compares to Earth's orbit. Start with Mercury, the innermost planet. Mercury circles the Sun at about 0.39 astronomical units, roughly 58 million kilometers from the star. That sounds close, and it is, in orbital terms, but remember our earlier model. If the Sun is a basketball, Earth is a bead 2 school buses away. Mercury would be another tiny bead parked only about 1 bus length from the ball. Still, there would be nothing in between. No ring of pebbles, no wall of fire, just empty space and sunlight getting harsher. Mercury itself is small, only about 4,879 kilometers across, roughly 38% of Earth's width. If Earth is a grape, Mercury is a chunky peppercorn. That little peppercorn spins strangely. One rotation on its axis takes about 58 Earth days, while one trip around the Sun takes only 88 Earth days. The result is a bizarre day-night rhythm. From sunrise back to sunrise on Mercury is about 176 Earth days. A single Mercury day lasts 2 Mercury years. The surface pays the price for that weird rhythm. Under the blazing sun, daytime temperatures climb to about 430 degrees Celsius. At night, with no atmosphere to hold the heat, temperatures plunge to around minus 180 degrees. That is a swing of more than 600 degrees across the same ground. A world that small, that close to the sun, with that slow spin, ends up as an oven that turns into a freezer every cycle. Move outward to Venus and everything changes again. Venus orbits at about 0.72 astronomical units, around 108 million kilometers from the Sun. In many ways, this planet is Earth's evil twin. Venus is about 12,104 kilometers across, around 95% of Earth's width. If you held 2 marbles side by side, one Earth and one Venus, you would be forgiven for thinking they were almost identical. But what matters is not just size, it is what a planet does with that size. Venus is wrapped in a thick atmosphere of carbon dioxide with clouds of sulfuric acid. The air pressure at the surface is about 92 times greater than Earth's. Stand on Venus if you could, and you would be crushed and cooked at once. Surface temperatures hover near 470 degrees Celsius, hot enough to melt lead. Probes that have landed there survived for minutes to a couple of hours before failing. Venus also spins the wrong way, at least relative to most planets. While Earth rotates from west to east, giving us sunrises in the east, Venus rotates from east to west. On Venus, the sun would appear to rise in the west and set in the east, if you could see it through the clouds. The rotation is unbelievably slow. One Venus day is about 243 Earth days long, yet Venus orbits the Sun in about 225 Earth days. A day on Venus is longer than its year. Then there is Earth, sitting at 1 astronomical unit. We will come back to its special mix of properties later, but for now just remember that we live at a distance where liquid water can exist on the surface, with a rotation period that keeps days and nights at a gentle length, and with an atmosphere and magnetic field that soften the Sun's violence without smothering us. Earth is the control case in this set of 4. Go one step farther out and you reach Mars at about 1.52 astronomical units, roughly 228 million kilometers from the Sun. Mars is about 6,792 kilometers across, roughly half the width of Earth. The red colour comes from iron oxide, essentially rust, coating rocks and dust. On a poster, Mars looks like a slightly smaller Earth with a different paint job. Up close, it is a thin-air desert. The average temperature on Mars is around minus 63 degrees Celsius, much colder than Earth. The atmosphere is very thin and mostly carbon dioxide. Without a strong blanket of gas, heat escapes quickly at night, and liquid water on the surface is unstable. Yet the planet is not boring. Mars hosts Olympus Mons, a volcano about 21 kilometers high, roughly 2.5 times the height of Mount Everest, and so wide that if you stood at its base, the summit would be beyond the horizon. Mars also has Valle Marineris, a canyon system about 4,000 kilometers long and up to 7 kilometers deep. If you stretched it across Earth, it would run from coast to coast of the United States. This tiny planet, half the size of Earth, carries geological features that make our own world look modest. Mars is an almost world, a planet that came close in some respects but fell short in others. Now pull back and look at these 4 worlds together. Same star, same general region. All rocky, all with some history of volcanoes, impacts, and surface reshaping. Yet their current faces could not be more different. Mercury is a blasted, swinging heat engine that alternates between furnace and deep freeze. Venus is a runaway greenhouse, a pressure cooker with lead melting temperatures and a backward spin. Earth is temperate, wet, full of chemistry and life. Mars is cold, thin-aired, sculpted by lost oceans and winds. On many diagrams, the inner planets are drawn almost touching, as if you could hopscotch from one to the next. In reality, even here, the gaps dominate. The distance between Earth and Mars, for example, is not fixed. It changes as both planets move. At their closest approach, they are still tens of millions of kilometers apart. At their farthest, hundreds of millions. Most of the time, nothing sits in those gaps except thin sunlight and the occasional passing asteroid. This is the first big lesson about the habitable zone, the region around a star where liquid water could exist on a planet's surface. Venus sits near the inner edge, Mars near the outer edge. Only Earth in the middle actually achieves long-term surface oceans, a stable atmosphere, and conditions that stay in a narrow band for billions of years. Distance helps, but it does not guarantee anything. Rotation, atmosphere, composition, magnetic field, and history of impacts, all of these combine to decide whether a world is a garden, a desert, or a hellscape. So when we say the inner planets are close together, what we really mean is that they are less far apart than the outer giants. To our senses and our machines, they are still separated by gulfs where you could hide entire miniature solar systems. 4 planets that look like a matched set on posters turn out to be wildly different experiments in planetary evolution, each one shaped by the same star in a different way. As we leave this deceptively simple inner neighbourhood, we are about to confront an even bigger shift. Past Mars, the diagrams usually show a crowded band of rocks called the asteroid belt, and then the first of the giants. The real story is stranger. The belt is not a wrecked planet, but a failed one, and beyond it waits a world so massive it reshaped the entire architecture of the system. That is where we head next. When most people picture the region beyond Mars, they imagine a wall of rocks. Movies have taught us to expect dense swarms of tumbling boulders, a chaotic belt that any heroic spaceship must weave through like a fighter pilot dodging enemy fire. The truth is almost disappointingly calm. The asteroid belt is there. It is real. It is full of rocky bodies that tell the story of our solar system's birth. But as a place, it is mostly more of the same thing we keep finding everywhere. Empty space. The belt sits between about 2.2 and 3.2 astronomical units from the Sun. That is a band roughly 150 million kilometers wide, wider than the entire distance from the Sun to Earth. Within that band there are millions of rocky objects. Some are a few meters across, some are hundreds of kilometers wide. Yet if you flew through the belt in a real spacecraft on a straight path, you would probably never see one with your own eyes unless you deliberately steered toward it. The rocks are spread out across such a vast volume that the average separation is enormous. The biggest resident of this quiet region is Ceres, now classified as a dwarf planet. Ceres is about 940 kilometers across, larger than many moons but tiny compared to any of the 8 major planets. If Earth is a full-size globe, Ceres is a marble sitting far away in the dark. For a long time, people imagined the belt as the shattered remains of a destroyed planet. The numbers do not support that story. If you could magically gather every asteroid in the belt, from Ceres down to the smallest rubble, and squeeze them into one sphere, the result would be underwhelming. The total mass would be only about 4% of the Moon's mass, not enough to build even a modest world. The belt is not the graveyard of a planet that died. It is the rubble of a planet that never quite formed in the first place. Something prevented the material there from merging into one large body. That something is waiting just beyond. Step outward again and you meet Jupiter at about 5.2 astronomical units from the Sun, more than 5 times farther away than Earth. This is the first of the giants. The word giant almost feels weak here. Jupiter is so big that we tend to say the facts once, nod, and move on without really feeling them. So let us slow down. Jupiter is at about 139,820 kilometers across. That is roughly 11 times Earth's width. If Earth is a marble, Jupiter is a basketball. That comparison sounds manageable until you think about volume. You do not just stretch Earth's diameter by a factor of 11, you fill a 3-dimensional space. More than 1,300 Earths could fit inside Jupiter's volume. Mass pushes the contrast further. Jupiter weighs in at about 318 times the mass of Earth. Put every other planet on a cosmic scale, from tiny Mercury up through Neptune, and Jupiter still outweighs them all combined by more than a factor of 2. When you say the solar system is dominated by the Sun, That is absolutely true. The star holds almost everything, but among the planets, Jupiter is the gravitational monarch, and its mass has shaped everything around it, including that belt of failed rock. Jupiter is not a scaled-up version of Earth. It does not have a solid surface that you could stand on. It is mostly hydrogen and helium, more like a small star that never ignited than like a big planet. If you tried to descend into Jupiter, you would fall through layers of gas that gradually turn into compressed fluid under crushing pressure. Somewhere deep inside there might be a rocky or icy core. We are not yet certain. What we know is that any spaceship plunging too deep would be crushed long before it found anything that felt like ground. Look at Jupiter through a telescope and you see bands and spots painted across its face. The most famous of these is the Great Red Spot, an enormous storm. Early astronomers saw it in the 1600s, and it is still raging today. This is a cyclone bigger than our entire planet. You could drop Earth into it and still have room left around the edges. Winds at the edge of the storm reach speeds of around 430 km per hour. This hurricane has been going for at least 4 centuries in a row. Jupiter spins extremely fast for a world so large. One day on Jupiter, from sunrise back to sunrise, is only about 9 hours and 56 minutes long. That rapid rotation flattens the planet slightly at the poles and bulges it at the equator. It also helps drive strong jet streams in the atmosphere, carving those coloured bands around the globe. This is not a calm, slow-turning gas ball. It is an engine. And then there are the moons. Jupiter has at least 79 known moons, with more still being found. The 4 largest, discovered by Galileo in 1610, are Io, Europa, Ganymede, and Callisto. In many ways, they are the real highlight of the Jovian system. They turn Jupiter into a miniature solar system of its own. Io is the closest of the 4 big moons, and it is wild. Io is the most volcanically active body we know. Its surface is constantly being resurfaced by eruptions. There are hundreds of active volcanoes blasting plumes of sulfurous material into space. The engine behind this activity is tidal heating. As Io orbits, Jupiter's immense gravity squeezes and stretches the moon, flexing its interior. The repeated flexing generates heat through friction, melting rock, and driving volcanoes. Europa orbits a little farther out and plays a subtler game. At first glance, it is the smooth icy sphere, crisscrossed with reddish cracks. Underneath that ice, scientists are confident there is a global ocean of liquid water, kept warm and fluid by the same kind of tidal heating that torments Io, just less violently. That hidden ocean might contain more water than all of Earth's oceans combined. In terms of raw liquid volume, this tiny moon may be the ocean champion of the solar system. Ganymede, the next one out, is the largest moon in the solar system. It is bigger than the planet Mercury. Ganymede is also unique among moons because it has its own magnetic field. That suggests a complex interior with layers of conductive material moving around, generating magnetism. It is not just a dead icy rock, it is a layered world with its own personality. Callisto, the outermost of the 4, is heavily cratered. Its surface preserves a record of impacts going back billions of years. While Europa and Io are being resurfaced and stirred, Callisto has been quietly collecting scars. It is like a fossil moon, showing us what the ancient outer solar system was throwing around. There are hints that even Callisto might hide an ocean deep below, a reminder that water in the outer system is not rare at all. It is almost standard equipment. Together, these moons show how Jupiter's gravity does more than hold objects in place. It kneads them, heats them, reshapes them, and in some cases may even create environments where life could exist. The giant that kept a planet from forming in the asteroid belt also lit up volcanic worlds and hidden oceans in its own neighbourhood, so the story of this region is one of control. The asteroid belt is not random rubble. It is material that Jupiter never allowed to grow up. The 4 big moons are not afterthoughts. They are worlds sculpted by the same gravitational hammer. By the time we leave Jupiter behind, it should be clear that this single planet has already rewritten the rules for everything around it. In the next part, we push even farther out to meet another ringed giant, 2 pale blue ice giants, and some of the strangest seasons and surfaces yet anywhere in our cosmic neighbourhood. Move outward past Jupiter, and you might think you already know how the rest of the story goes. Big planet, lots of moons, some stripes, repeat. But the outer half of the solar system refuses it to be a simple remix. Out here the rules twist. Planets float in rings of ice, moons keep underground oceans alive, and one of the giants has fallen so far onto its side that it rolls around the sun like a dropped bowling ball. The deeper you go, the stranger it sets. The next stop is Saturn at about 9.5 astronomical units from the sun. On the posters, Saturn is the flashy one. Big yellow world, iconic rings. In real numbers, Saturn is about 116,460 kilometers across, roughly 9.5 times the width of Earth. That alone would make it impressive. By volume, you could pack around 760 Earths inside. Yet Saturn has a surprising secret. It is so light for its size that in theory, if you could find an ocean large enough, Saturn would float. Its average density is lower than water. Like Jupiter, Saturn is mostly hydrogen and helium. There is probably a dense core buried deep inside, but everything above it is layers of gas and high-pressure fluid. Seen up close, Saturn wears bands and storms, but they are more muted than Jupiter's. The real star of the show is not the planet, it is the disk around it. Those rings are not a solid plate. They are made of billions of particles of ice and rock, ranging from dust grains to chunks the size of houses and mountains. From far away, the rings look broad and thick. In reality, they are incredibly thin compared to their width. In many parts of the main ring system, the thickness is measured in tens of meters. Imagine a sheet of paper spread out over a city. That is roughly the same kind of proportion. The main rings are divided into several labelled sections with gaps between them. One of the most obvious gaps, called the Cassini division, is about 4,700 kilometers wide. That is more than the width of the continental United States. Yet even there, the structure is not empty. It simply contains far fewer particles. Moons embedded in the rings and the gravity of Saturn itself sculpt these patterns, creating waves and lanes in the icy debris. Where did the rings come from? We do not know for sure. They might be ancient leftovers from the early solar system. Or they might be relatively young, perhaps only a few 100 million years old, made from a shattered moon or a captured comet that wandered too close and was torn apart by Saturn's gravity. What we do know is that the rings are slowly fading. Tiny bits of ice spiral inward and fall into Saturn's atmosphere. In a few 100 million years, the famous rings may be gone. Saturn itself carries one of the weirdest weather features anywhere. At its north pole sits a hexagon-shaped cloud system, about 30,000 kilometers across, a six-sided jet stream. We can simulate versions of this pattern in fluid experiments, but the exact details of how the atmosphere maintains such a clean geometric shape on that scale are still being worked out. It is like finding a perfect crystal pattern etched onto the top of a planet. Saturn has at least 146 known moons, more than any other planet we have found so far. Two of them have become icons in their own right, Titan and Enceladus. Titan is larger than the planet Mercury. It is about 5,150 kilometers across and wrapped in a thick orange atmosphere. This is the only moon in the solar system with an atmosphere denser than Earth's. The air is mostly nitrogen with some methane and other compounds. Sunlight filtering through the haze gives Titan a permanent twilight feel. At the surface, temperatures are around minus 179 degrees Celsius. At that temperature, water is rock hard. Ice behaves like stone. But methane, a gas on Earth, acts like water does here. On Titan there are rivers, lakes, and seas of liquid methane and ethane. Radar images from spacecraft show branching river channels carved into the icy ground, deltas, and smooth seas near the poles. Titan has its own version of a hydrological cycle, except it is a methane cycle. Methane evaporates, forms clouds, rains, and fills lakes. It is an alien version of something familiar. Enceladus is tiny by comparison, only about 500 kilometers across. You could drive around it in a day if there were roads. Yet this small moon turned out to be one of the most exciting discoveries in planetary science. Near its south pole, Enceladus has long fractures nicknamed tiger stripes. From these cracks, geysers blast water vapor and ice grains into space. Some of this material falls back as snow. Some of it escapes and helps feed one of Saturn's faint rings. When the Cassini spacecraft flew through those geysers, its instruments detected water, salts, and organic molecules. This told scientists that beneath Enceladus's icy crust there is a global or regional ocean of liquid water in contact with rock. In that dark ocean, tidal heating from Saturn's gravity keeps things warm enough for chemical reactions to run. On Earth, similar conditions at deep-sea vents support rich ecosystems without sunlight. Suddenly, This tiny moon became a prime candidate in the search for extraterrestrial life. Move outward again, and the pattern of giants shifts. At about 19 astronomical units you meet Uranus, slightly smaller than Saturn in width, around 50,724 kilometers, yet very different in personality. Uranus is not just another gas giant. It is what astronomers call an ice giant. Much of its interior is water, methane and ammonia in high-pressure forms, with only a smaller envelope of hydrogen and helium above. Look at Uranus and you see a pale blue-green disk with very subtle banding. It is almost too calm. For a long time we thought not much was happening there, but Uranus has a twist, literally. Its axis tilt is about 98 degrees. That means Uranus is essentially rolling around the Sun on its side. Its poles take turns pointing almost directly at the Sun during its 84-year orbit. Each pole spends about 42 years in continuous daylight, followed by 42 years of darkness. These extreme seasons are unlike anything on Earth. For decades, one hemisphere bakes in sunlight while the other sits in a long winter night. As the planet moves along its path, the sunlight slowly shifts until the roles reverse. The details of how the atmosphere responds to this slow, dramatic change are still being uncovered. But the basic fact remains. Uranus is a giant that fell over and never got back up. Finally, at about 30 astronomical units, we reach Neptune, slightly smaller than Uranus in size, around 49,244 kilometers across, but visually more dramatic. Neptune is a deep blue world with visible storms and bands. It is also an ice giant, with a similar internal mix of water, methane, and other compounds. Neptune has the strongest winds we have measured in the solar system, reaching around 2,100 kilometers per hour, faster than the speed of sound in Earth's atmosphere. These winds drive storm systems like this Great Duck Spot seen by the Voyager 2 spacecraft in 1989. What makes this even stranger is that Neptune receives only a tiny fraction of the sunlight Earth gets, hundreds of times less. To power such intense atmospheric motion, Neptune must have a significant internal heat source. The planet is glowing from within. Uranus and Neptune each have their own sets of moons and faint ring systems. Neptune's largest moon, Triton, circles the planet in the wrong direction relative to Neptune's spin, a clue that it was probably captured from elsewhere. Triton is geologically active with nitrogen geysers and may also hide an internal ocean. By the time you reach Neptune, you have seen 4 giants and a necklace of moons and rings very different from the rocky inner worlds, yet the same pattern keeps emerging. Enormous distances, vast empty stretches, isolated islands of complexity, Saturn's rings, Titan's lakes, Enceladus's plumes, Uranus's tilt, Neptune's winds. All of them are small intricate features riding on top of an overwhelming backdrop of space. So we have walked from scorched Mercury all the way out to deep blue Neptune. We have met volcano moons and methane seas and sideways planets. The shapes and colours changed, but one thing quietly grew with every step. The gaps, the empty regions between orbits expanded faster than the planets themselves. In the next part, we will stop visiting individual worlds and instead attack those distances directly, using road trips, light travel times and spacecraft speeds to see just how broken our intuition really is. By now we have walked through the planets like tourists hopping from one island to the next. Mercury, Venus, Earth, Mars, the giants, their moons, their rings. It all sounds like a packed neighbourhood. But if you stop focusing on the islands and start thinking about the water in between, something important happens. You realise that almost everything that exists in the solar system is not planets at all. It is distance. Raw, empty, almost featureless distance. The numbers that describe those gaps are so far beyond daily life that our intuition simply gives up. So in this part, we're going to gang up on your sense of scale with every trick we have. Let us start with an imaginary road trip. Picture our star sitting in the middle of Times Square in New York City, shining where all the billboards usually glow. Now you get in a car and drive west toward Los Angeles. The distance from New York to Los Angeles is about 4,500 kilometers, a long haul even by human standards. Along this highway we are going to place the planets. Wherever a planet's orbital distance matches some real point on the map, that is where we will drop it. Mercury goes down first. On this map it ends up near Philadelphia, about 140 kilometers from New York. That is the orbit of the closest planet to the Sun, a quick drive down the road. Venus lands somewhere around Pittsburgh, roughly 500 kilometers from Times Square. Earth sets up shop near Cleveland, about 750 kilometers out. Mars takes Chicago, roughly 1,200 kilometers from the starting point. So far, this feels manageable. The inner solar system fits neatly into the eastern half of the United States. Then the jump happens. Jupiter does not arrive until you have driven past Denver, roughly 2,500 kilometers from New York. Saturn sits in Nevada, close to the west coast, around 3,500 kilometers out. At that point, you have almost crossed the entire continent. Yet you are still not done. Uranus requires you to drive past Los Angeles and continue onto a boat. On this scale, it is somewhere in the Pacific Ocean. Neptune ends up near Hawaii, far out across the water. That one simple analogy carries a punch. Mercury through Mars, every rocky world fits comfortably between New York and Chicago. The gas giants and ice giants are scattered from the Rocky Mountains to Hawaii. The further out you go, the more the distances explode compared to the sizes of the worlds themselves. A planet that could hold hundreds of Earths inside it is still just a tiny dot on a map, measured in thousands of kilometers. Now drop the car keys and ask an even more brutal question. How long does light take to cross these gaps? Not a jet, not a rocket, light. Light travels at about 300,000 kilometers per second. That is fast enough to circle Earth 7 times in a single second. It feels instant to us. When you flip a switch, the room lights up without any sense of delay. From the Sun to Earth, light takes about 8 minutes and 20 seconds to arrive. That means every time you look at the Sun, with proper protection of course, you're seeing it as it was almost 9 minutes ago. If the Sun somehow vanished, Earth would still orbit empty space for more than 8 minutes, bathed in light that already left long before. Then the light would stop and gravity would change, both at once. Light reaches Mercury in about 3 minutes. It reaches Venus in around 6 minutes. Mars, on average, sits about 12 light minutes away. Jupiter is 43 light minutes from the Sun. Light takes around 80 minutes to reach Saturn, a bit over an hour and a quarter. To get to Uranus, the fastest thing in the universe, needs about 2 hours and 40 minutes. To reach Neptune, it needs around 4 hours. Think about what that really means. If you could sit on a hill near Neptune and somehow look back at the solar system with impossible eyes that can see across billions of kilometers, you would never see anything as it is. You would always be watching a highlight reel from hours ago. The movements of the inner planets would look sped up but also delayed, like a time-lapse played from a few hours in the past. Light travel time also sets a hard floor on how fast any information or object can move. Nothing can beat it. For a spacecraft, the trip times are far longer. The Apollo missions needed about 3 days just to reach the Moon, a mere 1.3 light seconds away. That is us crawling across a tiny fraction of a percent of the Sun to Neptune distance. Mars is already in a different league. Because both planets are moving, the distance between Earth and Mars changes all the time. At their closest, they are about 55 million kilometers apart. At their farthest, about 400 million kilometers. Spacecraft that travel from Earth to Mars usually need between 6 and 9 months. NASA's Perseverance rover, which landed on Mars in 2021, spent about 7 months making that journey. Jupiter is farther still. The Galileo spacecraft, launched in 1989, took about 6 years to reach orbit around Jupiter. Juno, launched in 2011, took 5 years. Saturn demands more patience. The Cassini spacecraft launched in 1997 and arrived in 2004 after 7 years in flight. No one has ever launched a dedicated mission to orbit Uranus or Neptune. The only close views we have are from Voyager 2, which flew past Uranus in 1986 and Neptune in 1989. It took 9 years to reach Uranus and 12 years to get to Neptune after its launch in 1977. Speeds can help your intuition here. The fastest human-carrying vehicle ever built was the Apollo 10 command module during its return from the Moon. It reached about 39,900 kilometers per hour. At that speed, you could go from New York to Los Angeles in about 6 minutes. It feels unthinkably fast. Yet even at that pace, it would take more than 40 days to reach the distance of the Sun from Earth, 4 years to get to Jupiter, 8 years to Saturn, 17 years to Neptune. The fastest machine we have ever built is the Parker Solar Probe, launched in 2018. At its closest approaches to the Sun, Parker reaches about 690,000 kilometers per hour. At that speed, you could cross the United States in about 7 seconds. Space becomes a blur. Yet even Parker would still need roughly 2.5 days to cover the Sun-to-Earth distance. about 2 months to reach Jupiter, about 4 months to reach Saturn, something like 9 months to reach Neptune. These numbers punch holes straight through the comforting illusion that our solar system is a tidy set of worlds that are conveniently close together. Even with extreme engineering, even with decades of planning, we still move through this system slowly compared to its size. Voyagers 1 and 2, launched in 1977, took about 40 years to reach the boundary where the solar wind yields to interstellar space. They are still not anywhere near another star, and will not be for tens of thousands of years. So when you hear that a planet is a few astronomical units away, or that a probe has crossed 1 billion kilometers, it is easy to let the numbers slide past. But behind those numbers is a stubborn reality. The solar system is not built on human scales. It is built on light-time scales, on billions of kilometers, on journeys measured in years and decades. The planets are not neighbors in a tight circle. They are tiny moving targets scattered through a volume where even our record-breaking machines barely crawl. And incredibly, we have still been talking only about the region inside Neptune's orbit. Out beyond that last blue giant, the story is not over. It is just beginning to fade into a different kind of darkness. There are belts of ice, demoted planets with hearts of nitrogen, elongated worlds spinning too fast for their own shape, and far beyond them a ghostly cloud of comets that stretches almost a light year into space. That is where we head next. When you reach Neptune, it is tempting to plant a flag and declare the tour complete. 8 planets, a few famous moons, a sense that we have reached the outskirts. In most textbook diagrams, that is exactly where the picture ends. A neat curve for Neptune, then maybe a few dots for distant icy bodies, then nothing. The trouble is, Neptune is not a wall. It is more like the last lamppost before the road disappears into fog. Beyond that lamppost, the solar system keeps going. It just changes personality. Step a little farther out and you enter the Kuiper belt. Think of it as the icy cousin of the asteroid belt, but stretched around the back of the solar system beyond Neptune. It begins around 30 astronomical units from the Sun, roughly where Neptune travels, and extends out to about 50 astronomical units. In plain numbers, that is a ring tens of billions of kilometers wide. Instead of mostly rock, the Kuiper belt is filled with objects made of ice mixed with rock. Water ice, methane ice, nitrogen ice, frozen chemistry from the early days of the solar system. Most Kuiper belt objects are small, a few kilometers across, dark and hard to see, but some are large enough to be worlds in their own right. The most famous is Pluto. For most of the 20th century, Pluto held a special place as the 9th planet. Discovered in 1930, it sat at an average distance of about 39.5 astronomical units, around 5.9 billion kilometers from the Sun. It takes Pluto about 248 Earth years to complete one orbit. That means since its discovery, it has not even made it once around the Sun. Pluto is about 2,377 kilometers across, smaller than Earth's moon. For decades, our picture of it was a blurry dot. Then in 2015, the New Horizons spacecraft flew past, and everything changed. The images that came back showed a world far more complex than anyone expected. Mountains of water ice rising 3.5 kilometers high, vast smooth plains of frozen nitrogen, dark cratered regions and bright young terrain. One heart-shaped feature called Tombor Regio dominates one side. The left lobe of this heart, Sputnik Planitia, is a basin filled with nitrogen ice. The surface there is divided into cell-like patterns, as if the ice is slowly churning. Warmer material rises in the center of each cell, and cooler ice sinks along the edges, much like a pot of thick soup simmering on a stove, that hints at internal heat slowly working through the crust, even at that incredible distance from the Sun. Pluto is not a dead frozen marble. It is active, reshaping itself. Pluto has 5 known moons. Charon is the largest, about half the width of Pluto itself. This is such an extreme ratio that some scientists consider the pair a double dwarf planet system, rather than a planet and a moon. Pluto and Charon both orbit a point in space that lies between them, like 2 dancers circling a shared center. The other small moons, Styx, Nix, Kerberos and Hydra, are irregular chunks that probably came from an ancient collision. As telescope technology improved, astronomers began finding other objects in the Kuiper belt with sizes similar to Pluto. One of them, Eris, is slightly smaller in diameter but more massive, and travels on a distant and stretched out orbit that averages about 68 astronomical units from the Sun. Discoveries like Eris forced a decision. Either we promote every Pluto-sized Kuiper Belt object to full planet status and watch the count rise into the dozens or hundreds, or we admit that we need a new category. In 2006, the International Astronomical Union defined the term planet in a stricter way. Under that definition, a planet must orbit the Sun, have enough mass to pull itself into a round shape, and have cleared its orbit of other debris. Pluto and its siblings failed the last test. They share their region with many other objects. Pluto was reclassified as a dwarf planet. The decision upset many people who had grown up with 9 planets, but scientifically it clarified the landscape. Pluto did not get smaller. We just got better at naming things. Other dwarf planets in the Kuiper Belt add their own flavours. Makemake is slightly smaller than Pluto and coated in frozen methane that gives it a reddish colour. Haumea is one of the strangest. It spins so quickly, completing one rotation in less than 4 hours, that centrifugal force stretches it into a rugby ball shape rather than a sphere. Haumea also has a ring system and at least 2 small moons. Eris, Makemake, Haumea, Pluto and many smaller bodies show that the outer ring is not just random gravel. It is a collection of complex icy worlds, each with its own geology and history. Yet even here the pattern repeats. The Kuiper Belt is not a solid wall. It is sparse. The objects are scattered through a huge volume. A spacecraft could fly through the region and never pass near anything interesting unless it was deliberately aimed. The emptiness still wins. The belt is a thin, lumpy halo wrapped around the outer planets, rich in stories but poor in density. And then the real vertigo begins. Beyond the Kuiper Belt lies something we have never seen directly, but almost every line of evidence says it is there: the Oort cloud. If the Kuiper Belt is a ring around the Sun's waist, the Oort cloud is a bubble that surrounds the entire solar system. It is thought to start around 2,000 astronomical units from the Sun and extend out to perhaps 100,000 astronomical units. 100,000 astronomical units is about 1.6 light years. That is roughly 1/3 of the distance to the nearest star. In other words, the Sun's gravitational influence does not end at Neptune or Pluto. It fades slowly, and small icy bodies can still be bound to our star at distances where the Sun is just another bright point in the sky. Beyond that, other stars start to tug more strongly, and the concept of our solar system's outer boundary becomes fuzzy. We call the Oort cloud theoretical because no telescope has ever imaged it directly. The objects are too small and too faint, and they sit too far away. Instead, we infer its existence from the behaviour of long-period comets. These are comets that dive into the inner solar system from all directions, not just the plane of the planets, and then take hundreds or thousands of years to return. Their orbits are so stretched and so randomly oriented that the simplest explanation is a distant spherical reservoir of icy bodies, occasionally nudged inward. Those nudges can come from many places: the gravity of passing stars, the tidal pull of the Milky Way itself, subtle disturbances over millions of years. When an Oort cloud object is disturbed just enough, it begins a long, slow fall inward. As it approaches the Sun, its ices warm and begin to vaporize, creating the glowing coma and tail that make comets spectacular. Some comets, like Halley's Comet, probably began life in this distant region before their orbits were altered into shorter loops by encounters with the planets. Estimates for how many bodies live in the Oort cloud are staggering. There might be trillions of icy objects larger than 1 kilometre across, spread through a volume so vast that the average separation between neighbours could be tens of millions of kilometres or more. If you stood on one Oort cloud object, you might not see any others with your own eyes. The sky would look almost empty. A faint sun far away, a sprinkling of stars, perhaps a slightly brighter band where our galaxy arcs overhead. The Oort cloud itself likely has structure, an inner, more disk-like region sometimes called the Hills-Kuppels cloud, and an outer, more spherical shell. That spherical shape explains why comets can arrive from any direction in the sky, not just from along the plane of the planets. It also reminds us that the tidy disk we drew for the solar system is only part of the story. The true gravitational domain of the Sun is more like a bubble drifting through the interstellar space. So where does the solar system really end? Is it at Neptune, where the last major planet travels? At the Kuiper Belt, where dwarf planets roam? At the heliopause, where the solar wind gives way to the thin gas between stars? or at the far edge of the Oort cloud where the sun finally loses its grip. Different definitions give different answers, but they all share the same punchline. Whatever boundary you pick, it lies far, far beyond the picture most of us grew up with. We live deep inside this structure, orbiting relatively close to the central fire, while the outermost members drift in cold darkness so distant that a radio signal would take years to reach them. The neat diagrams stop at Neptune because our pages are too small, not because the system actually ends there. In the next part, we will step back from objects entirely and look at the invisible geometry that keeps everything moving, from inner planets to distant comets, and see how a few simple rules can choreograph a system that large. Up to now, we have treated the planets like toys nailed in place on invisible tracks. They each have a distance, each has a size, and we walk from one to the next. Reality is sneakier. The solar system is not a static model. It is a moving pattern written in gravity and momentum. Every world is in permanent freefall, always falling toward the sun and always missing it. The shape of that endless miss is what we call an orbit. Imagine throwing a ball on Earth. Give it a gentle toss and it arcs and hits the ground. Throw it harder and it goes farther before falling. In your mind, keep giving it more speed. If you could somehow throw the ball fast enough, the ground would curve away beneath it as quickly as the ball falls. The ball would keep falling and never land. That is an orbit. A planet is a ball that was thrown sideways billions of years ago and has been falling around the sun ever since. When you first learn about orbits, you often see them drawn as circles. That is a helpful simplification, but it is still a lie of convenience. The real paths are ellipses, slightly squashed circles. In an ellipse, there is a point where the planet is closest to the sun, called perihelion, and a point where it is farthest, called aphelion. Earth's orbit is almost circular, so the difference is small. Mercury's is much more stretched out, so it spends part of its year close in and part much farther out. This shape has a crucial consequence. Planets do not move at constant speed. They speed up near perihelion and slow down near aphelion. A good way to think about this is with an old rule discovered by Johannes Kepler. If you draw a line from the sun to a planet and let time pass, that line sweeps out wedges of area. Equal time slices sweep out equal areas. The only way that can happen on a stretched path is if the planet zooms when it is close and crawls when it is far. There is another simple rule under all this. The farther a planet is from the sun on average, the longer it takes to complete one orbit. Mercury whips around in 88 Earth days. Earth takes 1 year. Jupiter needs about 12 Earth years. Neptune takes about 165. This is why the outer system feels frozen in deep time. Seasons crawl and centuries pass before a distant world even finishes one lap. The solar system is mostly flat as well as elliptical. Most planets travel in nearly the same plane, a thin disk we call the ecliptic. You can imagine it as the surface of an invisible table, with the sun at the centre and the planets sliding along that table. But not quite perfectly. Each orbit is tilted a little bit relative to Earth's path. That tilt is called orbital inclination. Mercury has the largest inclination among the 8 planets at around 7 degrees. Pluto's tilt is more than twice that, one of the reasons it behaves like an oddball dwarf planet rather than part of the main set. This invisible geometry matters whenever we try to send a spacecraft anywhere. You cannot just point at Mars and hit the gas. By the time you get there, Mars will have moved. Instead, you have to aim for where it will be and follow a path that takes advantage of orbital mechanics rather than fighting them. The most efficient way to move between 2 roughly circular orbits is something called a Hohmann transfer orbit. That sounds fancy, but the idea is simple. Picture a spacecraft starting in Earth's orbit. To go outward to Mars, you briefly fire the engines to speed up. That extra speed makes your path an ellipse that still touches Earth's orbit at one end, but now reaches out to touch Mars's orbit at the other. Then you cut the engines and coast. You are now in freefall on a stretched path that carries you outward and upward. When you finally intersect Mars's orbit, if the timing was right, Mars will be there. You fire the engines again to match speeds and drop into a new, nearly circular path around the Sun at Mars's distance, or to fall into orbit around the planet itself. Going inward toward Venus works in reverse. You fire the engines to slow down a little. That drops the far end of your path inward, creating an ellipse that dips closer to the Sun. You coast until you meet Venus at the inner intersection. Again, timing is everything. The target planet and the spacecraft must arrive at the meeting point together. Because both worlds are moving, there are only certain times when their positions line up in a way that allows this efficient transfer. Those periods are called launch windows. For Mars, good windows open roughly every 26 months. Miss one, and you may have to wait more than 2 years for another chance that uses a similar amount of fuel. Jupiter has launch opportunities about every 13 months. Mission planners live by these rhythms. Sometimes we need more than just an efficient transfer. Sometimes we need a slingshot. Gravity assists let a spacecraft steal a tiny bit of momentum from a massive planet to change its speed and direction without burning extra fuel. Voyager 2 used a rare alignment of the outer planets to swing past Jupiter, then Saturn, then Uranus, then Neptune, each time bending its path and boosting its speed with carefully planned flybys. The concept is easier than the math behind it. Imagine rolling a small ball past a moving truck. If the ball passes behind the truck on the side it is turning toward, the truck's gravity, or in everyday life, its bumper in a gentle tap can swing the ball around and fling it in a new direction, faster than before relative to the ground. In space there are no bumpers, only gravity. A spacecraft that dives behind Jupiter and exits on the forward side can leave the encounter with more energy relative to the Sun. From Jupiter's point of view, the change is microscopic. From the spacecraft's point of view, it is the difference between reaching the next planet or not. Orbits also influence each other in quieter ways. When one object circles the Sun in a time that forms a simple ratio with another, like 2 orbits for every one of the other body, their repeated tugs can build up over time. These are resonances. In the asteroid belt, resonances with Jupiter clear out certain orbital periods entirely, creating the so-called Kirkwood gaps. At those distances, any asteroid that tries to hold a stable orbit will feel regular gravitational kicks from Jupiter and eventually be nudged into a new path. There are also special balancing points where gravity and motion cancel in a useful way. These are called Lagrange points. For a planet and the Sun, there are 5 such locations where a small object can share the planet's orbit in a relatively stable way. Jupiter's leading and trailing Lagrange points host swarms of Trojan asteroids that travel 60 degrees ahead of and behind the planet, like 2 loose packs of scouts on the same racetrack. Earth has smaller Trojan companions of its own. Put all of this together, and the solar system becomes less like a random collection of marbles and more like a carefully structured racetrack full of lanes, speed limits and shortcuts, elliptical paths, inclined planes, resonances, and slingshots create a hidden network of routes. We live inside this invisible architecture. Every mission we launch, every comet we watch, every meteor shower we see is really just matter obeying a few simple rules written in gravity. Understanding that geometry turns the chaos into pattern. It explains why inner planets run fast and outer worlds drift slowly, why belts have gaps, why some moons are heated from within, and how a small machine built on Earth can navigate billions of kilometers using nothing more than a handful of engine burns and the pull of distant giants. In the next part, we will rewind time and see how this whole structure arose from a collapsing cloud of gas and dust, and how the same laws that guide today's orbit sculpted the solar system into its current shape. We have spent a lot of time walking through the finished product. Planets in their lanes, belts in their bands, comets on stretched paths. It is easy to forget that this whole clockwork has not always been here. Once there were no planets at all, no Kuiper belt, no Oort cloud, just a cold drifting cloud of gas and dust minding its own business in a quiet corner of the galaxy. To really understand the scale and structure we see today, we need to rewind 4.5 billion years and watch that cloud collapse. Picture a vast region of space 2 light years across, filled with thin gas and dust. To us, that sounds huge. On galactic scales, it is a small knot in one spiral arm. Within that knot, particles of hydrogen, helium, and heavier elements left behind by earlier generations of stars drift and collide at low speeds. For ages, nothing happens. Then something nudges the balance. Maybe a nearby giant star explodes and a shockwave ripples through the cloud. Maybe gentle gravitational instabilities slowly grow. Whatever the trigger, the result is the same. Parts of the cloud start to collapse under their own gravity. As the cloud falls inward, it spins faster. You can see the same effect when a figure skater pulls in their arms and speeds up. What began as a lazy rotation turns into a tighter spin. The collapsing material flattens into a disk with a dense, hot bulge at the center. That bulge is on its way to becoming our star. The disk around it is the raw material for everything else. At the center, density and temperature climb until hydrogen nuclei begin to fuse into helium. Fusion releases energy. The young star turns on. It starts blasting light and a fierce wind of particles into the surrounding disk. But before that wind clears things out, gravity and stickiness are hard at work. Tiny grains of dust bump into each other and cling together. Millimeter clumps become pebbles. Pebbles become boulders. Boulders merge into mountain-sized chunks. Over time, those chunks grow into objects tens and hundreds of kilometers across. These are planetesimals, protoplanets in a violent kindergarten. In the inner part of the disk, close to the newborn star, temperatures are high. Only metals and rocky materials can stay solid. Water, methane, and other volatile compounds exist as gas. That means the building blocks available here are limited to stuff that does not easily vaporize. The planetesimals in this region merge into smaller, denser worlds made mostly of rock and metal. That is the origin story of Mercury, Venus, Earth, and Mars. Farther out, beyond a certain distance, the heat drops enough that water and other volatiles can freeze into ice. Astronomers call this threshold the frost line. Outside the frost line, there is suddenly much more solid material to work with, because you get rocky grains plus icy grains. The cores that form here can grow several times more massive than any rocky inner planet, and they do it faster. Once those cores become big enough, their gravity starts pulling in gas directly from the disk. Jupiter and Saturn were the champions of this phase. Their cores, probably about 10 times Earth's mass in the early days, grabbed enormous envelopes of hydrogen and helium before the disk thinned. They became gas giants. Farther out still, Uranus and Neptune also built large icy cores, but by the time they were ready to drink, much of the gas was gone. They ended up as ice giants, big but not bloated. More ice and heavier elements, less pure gas. This whole process did not take long in cosmic terms. Maybe a few million years to ignite the star, tens of millions to build the main planets. By around 100 million years after the collapse, the broad architecture was in place. But the solar system was not yet the calm, well-separated set of orbits we see now. It was messy, crowded with leftover planetesimals. The giant planets were probably not where we see them today, and their gravity was about to rearrange everything. Jupiter especially does not sit quietly. Models of planetary dynamics suggest that in the early solar system the giant planets migrated. They traded angular momentum with the disk and with each other. Jupiter may have drifted inward toward the Sun, then outward again, like a heavy skater gliding toward the center of the rink, then being pulled back by interactions with other skaters. Saturn, Uranus, and Neptune likely moved outward as well. As the giants shifted, they scattered smaller bodies everywhere. Some planetesimals were flung into the inner solar system where they pelted the rocky planets in a long era of bombardment. Others were thrown outward into distant, elongated orbits, eventually forming the Kuiper belt and seeding the inner parts of what would become the Oort cloud. Some were ejected from the solar system entirely, turned into free-floating wanderers between the stars. On the inner worlds, this mess left scars. The heavily cratered surfaces of Mercury and the Moon are fossil record from that period. Even Earth, with its active geology and weather, still shows hints in ancient rocks and basins. For a time, impacts were common enough to boil oceans and reset climates. At the same time, those impacts likely delivered water and organic compounds to Earth. The ingredients for life arrived scattered on rocks and icy bodies that hit a cooling world again and again. In the asteroid belt, Jupiter's repeated gravitational tugs prevented the planetesimals there from ever merging into a single large world. Every time bodies tried to settle into certain orbits, resonances with Jupiter pushed them away. Over billions of years, collisions ground many of them down. Others were nudged into new paths. What remains is a population of survivors in orbits that are relatively safe from those resonances, plus a steady supply of escapees that become near-Earth, asteroids and occasional visitors to the inner system. In the distant Kuiper belt, Neptune's migration sculpted the structure we see today. Some objects were captured into resonances where they orbit the Sun a set number of times for every Neptunian year. Pluto is one of those objects, locked into a pattern where it completes 2 orbits for every 3 of Neptune's. That resonance keeps their paths from crossing in a dangerous way, even though their tracks in space overlap when drawn on a flat diagram. The Oort cloud, that ghostly bubble so far away, is the final archive of this chaos. Many of its bodies probably formed much closer to the Sun, in the region where the giant planets assembled. As those giants moved and scattered material, some small icy worlds were thrown onto extremely stretched orbits that never quite escaped the sun's pull. Over time, gentle tugs from passing stars and the galaxy itself rounded that population into a loose sphere. So when you look at the solar system today and see neat layers of small, rocky worlds, then a gap, then gas giants, then ice giants, then belts and clouds of ice, you are seeing the frozen aftermath of billions of years of gravitational negotiations. Nothing about the layout is random. It is the fossil of a particular history. Different starting conditions or different migrations could have produced a very different system. Maybe no Earth at all, maybe gas giants closer in, maybe no calm, habitable zone. The power of this story really hits when you remember that we now see other planetary systems around distant stars. Many of them look nothing like ours. Hot giants skimming just above their stars, chains of tightly packed super-Earths, empty inner regions with most of the mass far away. Our solar system is not a universal template. It is one outcome of common rules acting on particular initial conditions. The collapse of that ancient cloud turned a featureless patch of gas into a structured system that spans light years, with tiny habitable worlds tucked into safe pockets. In the next part, we will zoom in on some of the smaller leftovers from that process, the asteroids, comets, and meteoroids that still wander through the system, and see how they continue to remind us of our violent beginnings and our ongoing vulnerability. When the planets finished forming, the solar system did not sweep up every last piece of material into neat spheres. It left crumbs everywhere. Some of those crumbs are quiet fossils drifting in stable orbits. Others are bullets with our name on them, following the paths that cross the lanes of planets. To understand how fragile our little blue world really is, we have to meet these leftovers up close. Because the solar system we admire as a clockwork is also a shooting gallery, and Earth is not permanently off the range. Start with asteroids. These are rocky bodies that orbit the Sun but are too small to be called planets or dwarf planets. Most live in the main belt between Mars and Jupiter, where we have already visited. They range from mountain-sized chunks down to boulders and rubble heaps a few tens of meters across. There are probably millions larger than 1 kilometer across and countless smaller pieces. Despite the scary name, the belt is mostly empty. The danger comes not from a dense wall of rock, but from the few that wander out of their safe orbits. Asteroids are not all made of the same stuff. Many are dark and carbon-rich, called carbonaceous types. They make up the majority and probably preserve primitive material from the early solar system. Others are stony, made mostly of silicate minerals with some metal mixed in. A small fraction are metallic, rich in iron and nickel, likely the exposed cores of small worlds that we shattered by ancient collisions. These types are not just labels. They tell us about different layers and histories of early planet building. Jupiter's gravity sculpts the main belt as surely as it prevented a planet from forming there. At certain distances from the Sun, where an asteroid would circle in a simple rhythm with Jupiter, such as 2 orbits for every one of Jupiter's or 3 for every one, the repeated gravitational nudges become destructive. Over time, they kick objects out of those orbits entirely, leaving gaps in the distribution called Kirkwood gaps. The belt we see today is a pattern of survivors in regions where resonances are less dangerous. Not all asteroids stay politely in the belt. Some share orbits with planets, hanging out near gravitational balance points called Trojan regions. Jupiter has huge swarms of Trojan asteroids leading and trailing it in its orbit, like 2 loose packs of runners on the same track. Even Earth has a few Trojans, tiny companions that most people have never heard of. Others follow eccentric paths that bring them close to our planet. These are near-Earth asteroids. They are the ones that keep planetary defense scientists awake at night. We have started visiting these objects directly. Japan's Hayabusa missions and NASA's OSIRIS-REx mission flew to small asteroids, touched down briefly, grabbed samples and returned them to Earth. Inside those grains of dust and rock are minerals, water-bearing compounds, and organic molecules that date back to the solar system's birth. These missions are like time machines that bring pieces of the protoplanetary disk into our laboratories. They also teach us how loosely some of these bodies are held together. Many asteroids are not solid boulders, but rubble piles held by weak gravity. That matters when you plan to push one, because at some point, we will have to push one. In 2022, NASA's DART mission deliberately crashed a spacecraft into the small moon of an asteroid called Didymos. The impact changed the moon's orbit by a measurable amount. It was a proof of concept for kinetic impact, the idea that a high-speed spacecraft can nudge an asteroid onto a slightly different path given enough warning time. It was humanity's first real-scale experiment in moving a celestial body on purpose. Quietly, it might be the most important spacecraft we have built so far. Comets tell a different story. While asteroids are mostly rock and metal, comets are mixtures of ice, dust, and rock. They spend most of their lives in the cold outer reaches of the solar system. When one ventures inward, sunlight heats its surface. Ice turns directly into gas, dragging dust with it. A fuzzy cloud called a coma forms around the solid nucleus. Solar radiation and the solar wind then push this material away, creating the iconic tails that can stretch millions of kilometers. Comets often have two distinct tails, a dust tail that curves gently along the comet's path, and an ion tail made of charged particles that points directly away from the sun, no matter which way the comet is moving. The nucleus at the center of all this drama is usually just a few kilometers across, a dark, low-density object with an irregular shape. Spacecraft like the European Space Agency's Rosetta mission have sent back close-up images of comet surfaces. They show cliffs, pits, smooth plains, and a texture more like blackened snowbanks than spotless ice balls. Short-period comets have orbits that bring them back near the Sun in less than 200 years. Many of these come from the Kuiper belt and have been shaped into tighter loops by gravitational encounters. Halley's Comet, which visits the inner solar system roughly every 76 years, is the most famous. Long-period comets take hundreds of thousands or even millions of years to complete a single orbit. Their paths suggest an origin in the distant Oort cloud. These long-distance visitors are clues that the invisible outer reservoir really exists. As Kuiper comets make repeated close passes by the Sun, they lose their volatile ices. Eventually they can become dormant, dark bodies that look a lot like asteroids. The boundary between asteroids and extinct comets is blurry. Some objects we label as asteroids today might once have been blazing comets billions of years ago. From Earth's point of view, the important question is simpler. Does the orbit cross our path? When an asteroid or comet fragment is small, roughly pebble to boulder sized, and it enters Earth's atmosphere, we call it a meteoroid. Friction with the air heats it up, vaporizes its outer layers, and produces the bright streak we call a meteor. Most burn up completely, leaving nothing but a trace of ionized gas. On a clear night during a meteor shower, you can see dozens of these tiny cosmic grains getting erased in flashes of light. Meteor showers happen when Earth passes through debris left by a comet's orbit. It is like driving through a dusty lane once a year. If a fragment is large enough that part of it survives to reach the ground, that remnant is a meteorite. Meteorites come in three main types: stony meteorites made mostly of silicate rock, iron meteorites made of metallic iron and nickel, and stony iron meteorites that are mixtures of both. Some very primitive stony meteorites contain rounded inclusions called chondrules. These are droplets of once molten material from the early disk, frozen in time. In your hand, a meteorite is a literal piece of another world, sometimes of a world that never formed at all. Impacts have shaped Earth's history in ways that are hard to overstate. 50,000 years ago, a roughly 50-meter-wide object slammed into what is now Arizona, excavating a crater more than a kilometer across. In 1908, an object tens of meters wide exploded in the atmosphere over Siberia, flattening thousands of square kilometers of forest in the Tunguska event. In 2013, a smaller object about 20 meters across exploded over Chelyabinsk in Russia, shattering windows and injuring more than 1,000 people with flying glass. None of these were even close to the worst cases. 66 million years ago, a body about 10 to 15 kilometers across struck near what is now Mexico. The energy release was equivalent to billions of nuclear bombs. It triggered tsunamis, wildfires, and long-lived climate changes that darkened the sky and crashed food chains. Around 75% of species went extinct, including the non-avian dinosaurs. Mammals, which had been mostly small and marginal, took over many of the empty niches that followed. Our own existence is tied indirectly to that one terrible day. Right now, Earth is bombarded by about 100 tons of tiny dust and sand grains every day, mostly harmless. Larger meteoroids big enough to create bright fireballs arrive a few times a year. Objects in the tens of meters range that can cause regional damage hit every few centuries or millennia. City killers and civilization-scale impactors are rarer still, but they do not have a schedule. The universe does not owe us a grace period. So we watch. Telescopes on the ground and in space scan the sky for near-Earth objects, map their orbits, and project their paths decades into the future. Missions like DART test ways to nudge a dangerous rock if we find one with enough lead time. The recipe is simple in theory. Find it early, nudge it gently, let orbital mechanics do the rest. The hard part is the first step. Asteroids and comets are not just threats. They're also archives. Each one carries clues about the conditions in the disk where it formed, about the mixing of material in the young solar system, and about the delivery of water and organic molecules to the inner worlds. They are both bullets and history books. When we study them, we are not only learning how to defend ourselves, we are learning where we came from. In the next part, we will zoom back out to the star that holds all of this together, explore how its wind carves a bubble through the galaxy, and see how tides, seasons, and magnetic fields connect Earth to the power rest of the system in ways we feel every day without noticing. When we talk about the sun, then we usually think about light and warmth, sunrise, sunset, solar panels, summer heat. But our star is doing a lot more than just glowing in the sky. It is blowing a wind that fills a bubble bigger than every planet's orbit. It is tugging on oceans and moons and molten cores. Its tilt relative to our worlds quietly writes the script for every season you have ever lived through. The real influence of the sun is not just what you see, it is an invisible web of forces that shapes the entire system. Start with the solar wind. The sun is not a perfectly calm sphere. It is a ball of hot plasma, with charged particles constantly being hurled outward into space. That outflow is the solar wind. Near Earth, the wind usually races past us at speeds of between about 400 and 800 kilometers per second. It is incredibly thin, only a few particles in each cubic centimeter, far emptier than any vacuum chamber on Earth. But emptiness multiplied by a vast volume becomes power. As the solar wind rushes outward in all directions, it inflates a vast bubble in the surrounding galaxy called the heliosphere. Inside this bubble, the sun's magnetic field and particles dominate the environment. Far outside, the thin gas that fills the space between stars pushes back. The boundary where the pressure of the solar wind drops and interstellar space begins is called the heliopause. You can think of it as the frontier, where our star's direct influence ends and the rest of the galaxy takes over. Voyager 1 crossed that frontier in 2012, at a distance of about 122 astronomical units from the Sun, roughly 18 billion kilometers. Voyager 2 followed in 2018 at about 119 astronomical units. Even out there where the Sun is just another bright star, its wind had carved out a protective cavity. Beyond the heliopause, the spacecraft began to feel the denser, more chaotic plasma of the wider galaxy. The shape of the heliosphere is not a perfect sphere. The whole system is moving through the Milky Way at roughly 220 kilometers per second relative to the local gas. That motion compresses the heliosphere in front and stretches a tail behind, like the wake of a boat moving through water. So even at the largest scales, the Sun is ploughing through the galaxy, surrounded by its own bubble of influence. Closer in, gravity takes over as the main sculptor. Gravity is not just the force that keeps planets circling the Sun, it also tugs differently on near and far sides of objects. That difference is what we call a tidal force. On Earth, the Moon's gravity pulls more strongly on the side of the planet facing it than on the side turned away. The result is a pair of bulges in the oceans, one facing the Moon and one on the far side. As Earth rotates under these bulges, we experience two high tides each day. The Sun also raises tides on Earth, though they are smaller than the lunar ones. When the Sun and Moon line up, their tidal tugs add together, and we get unusually high tides and low tides. When they pull at right angles, the tides are milder. Even if you live far from the coast, those ocean sloshes, day in and day out, are a reminder that celestial mechanics is literally moving water on our planet. Tidal forces do not just shift water, they create friction and heat. As Earth spins beneath the tidal bulges, the ocean drags against the seafloor and the crust. That friction slows Earth's rotation very slightly. Our day is getting longer by roughly 1.7 thousandths of a second per century. That is tiny, but over hundreds of millions of years it adds up. When dinosaurs walked the Earth, a day was closer to 23 hours long. The energy lost from Earth's spin does not vanish. It is transferred to the Moon's orbit. The moon is gradually drifting away from us at about 3.8 centimeters per year. Laser measurements bouncing off reflectors left by Apollo astronauts have confirmed this slow recession. In the deep future, eclipses will look different because the moon will appear smaller in the sky. All of that traces back to tiny differences in gravity acting over long times. On other worlds, tides reshape entire moons. Io, the innermost of Jupiter's big moons, is trapped in a tight orbit deep inside Jupiter's gravitational well. As Io travels, Jupiter's huge gravity squeezes and stretches it again and again. Picture bending a credit card back and forth until it warms and snaps. Inside Io, that constant flexing generates heat through friction. The result is the most volcanically active body we know. Hundreds of volcanoes erupting, resurfacing the moon in bright yellows and reds. Europa, another Jovian moon, feels a gentler version of the same effect. Tidal heating there is strong enough to keep a global ocean of liquid water from freezing solid beneath its ice shell. On Saturn's moon Enceladus, tidal flexing powers geysers that blast water and ice into space. In both cases, gravity and motion are keeping oceans alive in darkness. A moon does not need to sit in the classical habitable zone if its planet's gravity is kneading it from within. Tidal forces can also lock rotations. Our moon always shows us the same face because it spins once on its axis for every orbit it completes around Earth. That one-to-one match is tidal locking. Over time, tides between Earth and the moon synchronize the moon's spin with its orbit. The same process acts on many moons in the solar system. It is why so many of them keep one hemisphere permanently facing their planet. Now mix gravity with tilt and you get seasons. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit around the Sun. That tilt, not our distance from the Sun, is why we have summer and winter. During part of our orbit, the northern hemisphere leans toward the Sun and receives more direct sunlight for longer each day. That is northern summer and southern winter. Half an orbit later, the roles reverse. Mars has a similar tilt, about 25 degrees. So it also experiences seasons, but its orbit is more elongated, so some Mars seasons are shorter and more intense. During southern summer, Mars is closer to the Sun, making it warmer and dustier in that hemisphere. Global dust storms have a habit of kicking up during those perihelion summers. Jupiter's tilt is tiny, only about 3 degrees, so it does not have pronounced seasons. Its weather is driven more by internal heat and rapid rotation than by changing angles of sunlight. Saturn's tilt is about 27 degrees, giving it strong seasonal effects. As the planet moves around its nearly 30-year orbit, different parts of the rings and atmosphere tip toward the Sun. Instruments on the Cassini spacecraft watched the hexagon at Saturn's North Pole change colour over the course of its mission as seasons shifted. Uranus takes the idea of tilt and breaks it. With an axial tilt of about 98 degrees, it is essentially lying on its pendenmamod. For more than 40 years at a time, one pole faces the Sun in nearly constant daylight while the other sits in darkness. Neptune, with a tilt similar to Earth's and a much longer year, experiences seasons that last about 40 years each. Even Mercury, which barely tilts at all, has a kind of orbital season, driven by its very stretched path around the Sun. At perihelion, it receives more than twice as much energy as at aphelion. All of these effects, tides, heating, locking, seasons, are different expressions of the same basic story. Gravity does not just hold things in place. Combined with motion, it redistributes energy. It slow spins, drags moons outward, melts ice under rock, and shuffles sunlight from pole to pole over long cycles. The Sun is at the centre of this pattern, but every world participates in the dance in its own way. When you feel a change in the weather, as your hemisphere tips into summer or winter, when you watch a high tide creep up a beach, when a solar storm creates an aurora over polar skies, you're feeling the solar system operate at human scale. These are the local ripples of forces that also shape binary dwarf planets, bend comet paths, and carve a bubble through the galaxy. In the next part, we will climb aboard the machines that have ridden those forces out into the dark. From early flybys to daring landings and long-lived rovers, we will follow the story of how fragile robots built on one small world have managed to explore so much of this vast system. For most of human history, everything we knew about the solar system came from squinting up at tiny points of light. Then, in one short burst of time by cosmic standards, we started doing something radically different. We began throwing small, fragile machines into the void and asking them to send back postcards. It is easy to take those postcards for granted now. Pictures of Saturn's rings, dunes on Mars, ice cliffs on comets. But every one of those images was a victory over distance, time, and the sheer indifference of space. The story really begins in the early 1960s. In 1962, a spacecraft called Mariner 2 flew past Venus. It was the first successful planetary flyby. For the first time, a machine built on Earth dipped into the space of another world and measured it directly. Mariner 2 found that Venus was not a steamy jungle hidden under clouds, as some had hoped, but an inferno with a thick carbon dioxide atmosphere and crushing heat. Romance gave way to reality. The next big step came in 1965, when Mariner 4 flew past Mars and returned the first close-up photos of the red planet. They showed a dry, cratered landscape. No canals, no obvious vegetation, just a world that looked unsettlingly dead. Those early missions broke a psychological barrier. The planets were no longer unreachable lights. They were places we could visit, even if only in passing. In the 1970s, we started going farther and heavier. Pioneer 10 and Pioneer 11, launched in 1972 and 1973, blazed a trail to the outer planets. Pioneer 10 became the first spacecraft to pass through the asteroid belt and the first to reach Jupiter. Pioneer 11 followed, then went on to Saturn. Their cameras and instruments showed the giant planets in detail for the first time. Jupiter's belts and storms, Saturn's rings seen not as a thin band but as complex structured systems. Then came the Voyager twins. Launched in 1977, Voyager 1 and Voyager 2 were designed to take advantage of a rare alignment of the outer planets. By using gravity assists, they could hop from one giant to the next like stones skipping over the surface of a pond. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, then arced up out of the planetary plane on its way to interstellar space. Voyager 2 took the Grand Tour, Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989. No spacecraft has visited Uranus or Neptune since. The images and data from the Voyagers rewrote textbooks. They revealed volcanic eruptions on Io, a possible ocean under Europa's ice, complex ring structures, and strange moons that no one had imagined. Triton at Neptune with geysers of nitrogen, Miranda at Uranus, with jumbled cliffs that looked like a cut-and-paste experiment. The giants were no longer smooth pastel balls, they were dynamic worlds with families of bizarre satellites. The Voyagers did not stop when the flybys ended. Their paths carried them outward, through the outer reaches of the heliosphere. In 1990, at the request of Carl Sagan, Voyager 1 turned its camera back toward home from about 6 billion kilometers away and took the famous pale blue dot image. Earth appeared as a faint speck in a scattered sunbeam, less than a pixel across. Then the cameras were turned off to save power. The spacecraft kept going, measuring plasma and magnetic fields. Decades later, they would be the first human artifacts to cross the heliopause into interstellar space. While the Voyagers were heading out, other missions were choosing to stay and orbit. Galileo, launched in 1989, arrived at Jupiter in 1995 and became the first spacecraft to circle a giant planet for years. It made repeated close passes of the Galilean moons, sensing the interior structures of Europa, Ganymede, and Callisto. The evidence it gathered for global oceans beneath ice shells transformed those moons from curiosities into prime targets in the search for life. Saturn received similar treatment from Cassini. Launched in 1997 and arriving in 2004, Cassini spent 13 years in the Saturn system. It flew through ring gaps, dipped close to moons, and watched the planet's seasons slowly turn. Cassini revealed new moons hidden in the rings and intra-watt wave patterns in the ring material itself. Its radar mapped Titan's lakes and rivers of liquid methane. Its instruments tasted the geysers of Enceladus and found water vapor, salts, and organic molecules. The Huygens probe carried by Cassini detached and descended through Titan's orange atmosphere in early 2005. It parachuted down and landed on a surface strewn with ice pebbles, sending images and data until its batteries died. For a brief time, we had a weather report from a moon with methane rain under an alien sky. Cassini itself ended its mission by plunging into Saturn's atmosphere in 2017. That dramatic finale was not theatrical. It was a way to ensure the spacecraft could not accidentally contaminate any potentially habitable moons in the far future. Farther out, the New Horizons mission took up the mantle of firsts. Launched in 2006, it flew past Jupiter for a gravity assist and then spent nearly a decade crossing the outer system. In July 2015, it finally swept past Pluto at over 13 kilometers per second. For a few hours, all of our hopes about that distant world rode on one pass. The images it sent back stunned scientists and the public alike. Glaciers of nitrogen ice, mountains of water ice, a young active surface in places with few craters, more complexity than many had expected from such a small cold body. After Pluto, New Horizons continued into the Kuiper Belt and flew past a small object now named Arrokoth in early 2019, giving us our first close look at a pristine Kuiper Belt relic. Meanwhile, Mars quietly became the busiest destination in the solar system. The Viking landers touched down in 1976, performing the first successful soft landings and experiments on the Martian surface. In 1997, the Pathfinder mission delivered the Sojourner rover, a small-wheeled robot that trundled a few meters from its lander and sent back images and data. It proved that driving on another planet was possible. Spirit and Opportunity, twin rovers that landed in 2004, were designed for 90-day missions. Spirit lasted until 2010. Opportunity worked until 2018, travelling more than 40 kilometers across the Martian surface. They found evidence of ancient water and varied geology, confirming that Mars once hosted environments that could have been friendly to life. Curiosity, which landed in 2012, is still operating. It carries a mobile chemistry lab, drilling into rocks, baking samples, and reading the gases they emit. Perseverance, which arrived in 2021, is exploring an ancient lake bed and caching samples that a future mission may bring back to Earth. Perseverance brought a companion, a small helicopter called Ingenuity. In the thin Martian air, Ingenuity made the first powered flights on another world. It was a technology demonstration that turned into an extended scouting mission, hopping ahead of the rover and helping plan routes. Each of these missions had to fight the same brutal scale we've been talking about. Years of planning and construction on Earth, months or years in cruise, then minutes of terror during atmospheric entry, deployment of parachutes or retro rockets, and landing. Then, if everything worked, a slow drip of data over radio links that can take minutes or hours to cross the void. Engineers and scientists back home watched time-delayed graphs and pixelated images, trying to infer the state of a machine that might have just bounced or burned or landed perfectly. What all of them together show is that despite the solar system's size, we are not completely confined to our one rock. We have orbited every giant planet except Uranus and Neptune. We have landed on Venus, Mars, the Moon, Titan, asteroids and comets. We have flown through plumes from hidden oceans and skimmed the edges of rings made of ice and dust. We have sent probes far beyond the planets, out through the heliosphere and into the interstellar medium. And yet, even with all those triumphs, humans themselves have only walked on one other world, the Moon, and only briefly. No person has yet stood on Mars, felt the sunlight filtered through its thin sky, or looked up at Phobos and Deimos with naked eyes. For all our robotic reach, we are still a species that lives entirely on one fragile planet near the middle of the system. That contrast is important. We have proven that we can design machines that cross billions of kilometers and survive in environments far more hostile than Earth. But the place that supports us directly remains one small world at one particular distance from the Sun. In the next part, we are going to turn our attention back to that world, look closely at what makes it uniquely stable and habitable, and then ask the obvious question. Are there other Earths out there circling other stars, or are we living on a kind of cosmic exception? For an hour and a bit of cosmic storytelling, we have treated Earth as just one more stop on the tour. Third planet, one astronomical unit from the Sun, modest size, blue and on white marble. That is technically true, but emotionally it is ridiculous. Earth is not just one more data point. It is the only place we know where rocks learn to think about the universe. To really feel the scale of the solar system, you need to feel how wildly specific our home is, and how hard it has been to find anything quite like it anywhere else. Start with distance. There is a region around any star where liquid water can exist on the surface of a rocky planet. Too close and water boils away, too far and it freezes solid. Astronomers call this the habitable zone. Our world sits comfortably within that band. Venus orbits just inside its inner edge and turned into an acid pressure cooker under runaway greenhouse heating. Mars orbits near the outer edge. It is cold, thin-aired, and mostly dry. Earth, for billions of years, has been in the sweet spot where liquid water can pool on the surface and stay there. But distance alone does not guarantee a living world. Mars is technically in the habitable zone, and it is still a frozen desert. The magic comes from layers of coincidence piled on top of that correct distance. Earth is the right size, big enough to hold onto a thick atmosphere and maintain a molten core, not so big that it turns into a mini Neptune wrapped in suffocating gases. That molten iron core powers a magnetic field that stretches out into space and deflects much of the charged particle wind from the sun. Without that shield, the solar wind would slowly erode the atmosphere. Mars shows you the alternate timeline. Smaller, cooled faster, lost much of its field, then much of its air. Earth's crust does something else unusual. It moves. Plate tectonics is the slow shuffle of large pieces of crust across the surface, colliding, diving, and resurfacing. This process recycles carbon between the atmosphere, the oceans, and the interior. Volcanoes release carbon dioxide. Weathering and ocean chemistry bury it again. Over long timescales, this acts like a thermostat. When the planet gets cooler, volcanic gases accumulate and trap more heat. When it gets warmer, weathering speeds up and pulls more carbon out of the air. The result is a climate that has stayed within life-friendly limits for billions of years despite big external changes. Now look up at the night sky and find the second brightest object after the sun. Our moon is weird. Not in a small, pretty way. In a dynamic planetary physics way. For a rocky planet of Earth's size, having such a large moon is uncommon among the worlds we see in our own system. The leading theory says that early in Earth's life, a Mars-sized body slammed into our planet. The impact was violent enough to melt both worlds and throw a ring of debris into orbit. That debris eventually clumped into the moon. This catastrophe had 3 enormous consequences. It gave Earth its current axial tilt, which creates moderate regular seasons. It melted and differentiated the planet, sending heavy iron, nickel to the core and lighter rock to the surface, helping to set up the magnetic field. And it gave us the moon itself, whose gravity stabilizes Earth's tilt over long timescales. Without that stabilizing weight in the sky, Earth's axis could wander chaotically over millions of years, swinging between almost no tilt and extreme tilt. That would drive brutal climate swings, ice sheets creeping far toward the equator, deserts where oceans used to be. Life might survive, but complex land-based civilization would have a harder time. The moon also creates tides. Twice a day it draws the oceans into bulges that creep across the coasts. In Earth's early history, when the moon was closer and tides were stronger, those rising and falling shorelines may have created countless shallow pools and mixing zones, perfect laboratories for chemistry that does not quite count as life yet. The exact role of tides in life's origin is still debated, but the timing and the environment line up intriguingly. Then there is water. Earth has the right amount. Not a global ocean world with no dry land, not a desert with only scattered pockets. About 70% of the surface is covered in water, leaving continents exposed. That balance helps drive the carbon cycle, weather patterns, and a complex web of ecosystems on land and sea. Too much water and plate tectonics may be suppressed. Too little and erosion and nutrient cycles would look very different. Our atmosphere is another tightrope act. Mostly nitrogen and oxygen, with a thin seasoning of greenhouse gases like carbon dioxide and methane. The oxygen is especially strange. For the first 2 billion years or so, Earth's air contained almost no free oxygen. Then tiny organisms figured out photosynthesis and started using sunlight to split water and carbon dioxide, releasing oxygen as waste. At first, this was a catastrophe for the microbes that found oxygen toxic, but slowly the planet adjusted. Iron rusted, new metabolic pathways evolved. Eventually, complex life learned to breathe this reactive gas and turned it into a powerhouse fuel. Viewed from far away, that oxygen would be a screaming clue that something unusual is happening here. Gas that reactive does not linger unless something is constantly replenishing it. That is one of the reasons astronomers hope to study exoplanet atmospheres. Finding a mix of gases out of equilibrium, like abundant oxygen alongside methane, would be a strong hint of active chemistry or even biology. so that is Earth's resume. Right distance, right size, long-lived magnetic shield, active plate tectonics, a large stabilizing moon, abundant but not overwhelming water, an atmosphere reshaped by life itself. None of these features is impossible elsewhere, but the combination is tight enough that we have not yet found another example. We have been looking. Since the mid-1990s, astronomers have discovered thousands of planets around other stars. The Kepler Space Telescope, launched in 2009, stared at a patch of sky and watched for tiny dips in starlight when planets passed in front of their stars. From those dips, it could infer sizes and orbital periods. Kepler showed that planets are everywhere. On average, most stars seem to have at least one. The census is wild. There are hot giants that orbit closer to their stars than Mercury does to the Sun. Super-Earths that are bigger and heavier than our world, but smaller than any gas giant in our system. Mini-Neptunes, rocky cores wrapped in thick gas layers, hugging close to stars. Planets in double star systems, circling both suns at once. Planets on eccentric paths with wildly changing seasons. The universe is not short on creativity. Hidden in that zoo are planets that look more familiar. Worlds roughly Earth-sized, receiving about the same amount of energy from their stars, orbiting in the so-called habitable zones. Some circle stars smaller and cooler than the Sun, some circle stars more like our own. A few are tantalizing, but our instruments are not quite good enough yet to read their atmospheres in detail. We can see that they exist. We cannot yet tell if they have continents, oceans, or air you could breathe. The James Webb Space Telescope is starting to nibble at this frontier. By studying the light of a star as a planet crosses in front of it, astronomers can tease out the faint fingerprints of gases in the planet's atmosphere. For now, most of the worlds we can analyze this way are big and hot. But as techniques improve, the dream is clear. Find a small rocky planet in the right zone, detect water vapor, maybe detect oxygen or other potential biosignatures, and know that somewhere on that distant world, chemistry went weird in the same way it did here. Until that day, Earth sits alone in our confirmed list. There may be millions or billions of true cousins scattered through the galaxy, but from our current vantage point, our planet is still the only place with oceans, forests, traffic jams, playlists, and people arguing about pizza toppings. That uniqueness is not a mystical statement. It is a temporary observational statement, but it has weight. Understanding how specific Earth's conditions are does two things at once. It fuels the search for other worlds, because we now know what features to look for, and it sharpens our sense of responsibility, because this planet is not just one more rock among many in our experience. It is the only habitable environment we can walk into without a pressure suit. If we wreck its climate or its ecosystems, there is no spare waiting in the next orbit over. In the next part, we will stretch the timeline instead of the distance, zooming out from Earth's few billion years of habitability to the entire lifetime of the Sun and the universe. The goal is to put our brief moment on this one rare world into the enormous flow of cosmic time and see what that perspective does to everyday worries. We have spent a lot of time stretching your sense of distance, planets as far apart as cities on different continents, comets taking centuries to loop once around the Sun, but there is another dimension where our instincts break even faster: time. When you zoom out far enough, the entire history of human civilization collapses into a thin scratch on the surface of cosmic time. And that tiny scratch sits inside an even narrower window where Earth is calm enough and quiet enough for beings like us to exist at all. The universe is about 13.8 billion years old. Earth formed around 4.5 billion years ago, roughly 1/3 of the way through that story. For the first 9 billion years after the Big Bang, there was no Earth, no Sun, no solar system, just earlier generations of stars being born, burning, exploding and seeding space with the heavier elements needed to build planets and people. Our system is a late arrival. Life on Earth appeared surprisingly quickly once conditions allowed it. By about 3.8 billion years ago, the planet had cooled enough for oceans to form, and simple single-celled organisms were already leaving chemical traces in ancient rocks. For roughly 2 billion years, those organisms dominated. No forests, no animals, no bones, just microscopic life quietly rewriting the atmosphere and the chemistry of the oceans. Modern humans, Homo sapiens, have existed for about 300,000 years. That is around 0.007% of Earth's history. All of recorded human history from the first writing on clay tablets to your phone right now spans about 5,000 years, roughly 0.001% of the planet's story. Your own lifetime, if you live 80 years, is such a thin slice that compared to the age of the universe, it is effectively a numerical rounding error. And this is only the past. The future dwarfs all of it. Our sun is about halfway through its comfortable middle age. For roughly another 5 billion years, it will continue fusing hydrogen into helium in its core, gradually growing a bit brighter over time. That slow brightening matters. In a few 100 million to a billion years, the increased sunlight will likely push Earth into a moist or runaway greenhouse state. Oceans will shrink or boil, weathering cycles will change, and complex life as we know it may find the planet increasingly hostile long before any dramatic explosion. Farther ahead, around 5 billion years from now, the sun will run out of hydrogen in its core. Fusion will shift into a shell around the core. The outer layers will expand and cool. Our star will swell into a red giant hundreds of times larger than it is today. Mercury and Venus will almost certainly be engulfed. Earth's fate is less certain on the details and almost certainly bad on the outcome. Even if the planet is not swallowed outright, its surface will be scorched, its mantle melted, its atmosphere stripped. Whatever is left will not be a blue world with clouds and oceans. After a relatively brief red giant phase, the sun will shed its outer layers into space, creating a glowing shell of gas called a planetary nebula. At the center, the core will remain as a white dwarf, a hot, dense object about the size of Earth but with roughly half the sun's current mass. Over trillions of years, that white dwarf will slowly cool and fade, eventually becoming a dark, cold remnant called a black dwarf. The solar system at that point will be a graveyard. Planets, asteroids and comets still orbiting, but in eternal night around a dead ember. Zoom out further and things become even more extreme. The universe seems to be not only expanding but accelerating in its expansion. Over enormous timescales, that acceleration means galaxies drift farther and farther apart. New stars form more slowly as gas runs out. Old stars die. Black holes evaporate over unimaginably long periods. In many models, the universe ends in a featureless state where matter and energy are so thinly spread and so low in temperature that nothing interesting can happen. This scenario is called heat death, and the timescales involved are numbers like 10 to the power of 100 years, a 1 with 100 zeros after it. Human language almost gives up at that point. Within that vast sea of time, our current era is a tiny, oddly special patch. Not too early, when heavy elements were scarce and planets were rare. Not too late, when stars have burned through their fuel. We live in a phase where long-lived stars, stable planetary orbits, and rich chemistry are all possible at once. On Earth, that cosmic timing intersects with geological timing. Our planet is still geologically active, still has a magnetic field, still has plate tectonics, still has a thick atmosphere and abundant liquid water. Those conditions will not last forever, and that is without counting the dice rolls of catastrophe. Asteroid impacts, which we talked about earlier, have already punctuated Earth's history with mass extinctions. The dinosaur-killing impact 66 million years ago was not a unique kind of event. It was just the most recent example of a big one. Over hundreds of millions of years, there have been others. There will be more, unless we learn to prevent them. Beyond rocks, there are more exotic threats. Certain massive stars end their lives not just as supernova explosions, but as gamma-ray bursts, focused beams of extremely energetic radiation. If one of those beams happened to sweep across Earth from a relatively nearby star, it could strip away the ozone layer in seconds. That would allow harmful ultraviolet radiation from the sun to reach the surface unfiltered, with devastating effects on living organisms. The good news is that gamma-ray bursts are rare, and most seem to point their beams away from us. The bad news is that if one ever did line up, there would be no warning. The beam travels at the speed of light. Rogue black holes are another theoretical hazard. Gravitational interactions in dense star clusters can occasionally fling black holes out into the wider galaxy. A black hole drifting through the Milky Way is invisible in the dark unless it passes through gas or close to a star. If such an object wandered through our solar system, its gravity could distort planetary orbits, destabilize the Oort cloud, and send showers of comets inward. The odds of a direct encounter are very low because space is so empty, but low is not zero on long enough timescales. Even our own star can give us trouble from time to time. Solar storms, especially large eruptions called coronal mass ejections, can hurl billions of tons of plasma and magnetic field into space. When such a cloud hits Earth, it can trigger beautiful auroras, but also damage satellites and overload power grids. In 1859, the Carrington event caused telegraph wires to spark and fail and produced auroras so bright people could read newspapers at night. If a storm of that magnitude or larger hit our modern technology-dependent civilization, the disruption could be enormous. Farther down the calendar, there is the slow gravitational ballet of galaxies. In about 4 billion years, the Milky Way and the Andromeda Galaxy will start to merge. Stars are so widely spaced that very few will collide directly, but the gravitational chaos will reshape orbits on large scales. The outer comet reservoirs around both stars will be stirred violently, sending waves of comets into their inner systems. All of this may happen around the same time our Sun is starting its red giant transformation. From the perspective of any future Earth life, if there is any left, it will be a very bad time to live in this neighborhood. So where does that leave us? Not at the center of space, not at the center of time, not under any special protection. We live in a window of a few billion years on one small world where conditions have lined up to make complex life possible. Inside that window, the last few thousand years have seen the rise of civilizations capable of science and technology. Inside that thin slice, the last few centuries have given us the tools to understand our cosmic situation and, crucially, to start protecting ourselves from some of the dangers. That combination awareness plus agency is new. For almost all of Earth's history, life could only endure whatever the cosmos threw at it. Now, a species that evolved from that life can discover potentially hazardous asteroids, model supernova threats, harden power grids against solar storms, and think seriously about moving life beyond its planet of origin. We are still vulnerable to many things, but we are no longer entirely passive. Seeing our moment as a fragile, finite window does not have to lead to despair. It can lead to focus. The universe will keep expanding whether or not we build telescopes. The sun will evolve whether or not we solve climate change. But within the tiny fraction of cosmic time where we exist, we get to decide what kind of story plays out on this pale blue dot and what kind of traces we send into the wider dark. In the final part, we will pull all of these threads together, the distances, the timelines, the dangers, the explorations, and the mental revolutions that took us from a flat Earth under a small sky to a planet circling an ordinary star in an immense universe, and ask what that knowledge is really for. When you zoom out far enough, everything we have talked about in this documentary collapses into one tiny story. All the orbits and launch windows, all the volcanic moons and icy giants, every mission we have ever flown, and every question we have ever asked about our solar system, they all unfold on a stage that is unimaginably small compared to the wider universe. You live on a moving speck that circles an ordinary star inside an ordinary galaxy, in a universe that will go on long after our star cools and the last spacecraft falls silent. The scale is absurd, and yet somehow you and I are here, thinking about it together. That is the strangest part of all. For most of human history, nobody knew any of this. To our ancestors, the universe was a bowl of stars stitched to the sky, turning around a flat or slightly curved Earth. The ground felt still and solid underfoot. The heavens moved. So of course we put ourselves in the center. Philosophers in ancient Greece built elaborate models with crystal spheres and nested shells to explain the motions of the wandering lights, the planets. Those models were wrong in almost every physical detail, yet they were a first attempt at something bold. A story about everything. Then the solar system started to push back. The motions of the planets refused to fit clean circles. They stalled, reversed, sped up, slowed down. Astronomers piled epicycle on epicycle, circles on top of circles, to patch the old model. It worked just well enough to hang on. Then a Polish cleric named Nicholas Copernicus quietly flipped the diagram. Put the star in the middle. Let Earth be a planet like the others. He did not yet have perfect evidence. What he really had was a simpler story that fit the data with less strain. Over the next century and a half, the universe cracked open. Johannes Kepler showed that planets travel in stretched ellipses, not perfect circles, and that their speeds adjust with distance in precise mathematical ways. Galileo turned a crude telescope toward the sky and saw 4 moons circling Jupiter, proving that not everything revolves around us. He saw phases of Venus that only made sense if Venus circled the star. The old crystal spheres shattered. Then Isaac Newton came along and did something even more radical. He showed that the same gravity that makes an apple fall describes the arcs of planets and comets. The solar system was no longer a special clockwork built from separate rules. It was just physics, all this way out. Once you accept that idea, the shrinking of our importance never really stops. The Milky Way turns out to be a flattened disk of hundreds of billions of stars, 10 times larger than the farthest reach of our Oort cloud in every direction. Our star is not near the centre. It is out in the suburbs, circling once every few 100 million years. Those faint smudges in old telescopes, the so-called spiral nebulae, turn out to be other galaxies entirely. The observable universe stretches tens of billions of light years in every direction and contains perhaps 2 trillion galaxies. On that map, our solar system is not a dot. It is too small even to draw. You might think this relentless demotion would make existence feel hopeless. You are smaller than you thought, less central than you hoped, more temporary than your instincts would like. But that is only one way to read the story. There is another. In this reading, the fact that a small primate on a small planet around a small star can work out the age of the universe, and the structure of the solar system is not depressing at all. It is astonishing. From this tiny, fragile platform, we have reconstructed a history that stretches from the Big Bang to the present. We have mapped orbits so precisely we can land a spacecraft on a comet and fly a probe through the geysers of Enceladus. We have taken our own homeworld and turned it into data and reflection. At some point along the way, we decided not to keep that understanding to ourselves. We started leaving messages for anyone who might pass by billions of years from now, long after our languages and nations and arguments are gone. In the 1970s, 2 small spacecraft called Pioneer 10 and Pioneer 11 were launched toward the outer planets. Each carried a metal plaque engraved with a human figure, a map of nearby pulsars, and a sketch of our solar system with a little arrow at the 3rd planet. It is an absurdly optimistic gesture. The chance of any alien civilization finding either probe is essentially 0. Space is just too big. But we sent them anyway. A few years later, the Voyager missions took that impulse and turned it into art. Each Voyager probe carries a golden record, a copper disc coated in gold sealed in a metal case bolted to the spacecraft like a time capsule. On that disc is a compressed portrait of Earth, music from many cultures, greetings in dozens of languages, sounds of rain and heartbeats and waves, images of mountains, cities, forests, families, mathematics, DNA, and planetary landscapes. If an intelligent species ever finds one of these records and figures out how to decode it, they will see what we looked like at a particular moment in our history. But once again, the odds are microscopic. The more realistic audience is us. Knowing that we were sending a message to the universe forced us to ask a hard question. If we have only one record to represent humanity, what should go on it? What parts of ourselves are we proud of? What do we hope will still matter after our star has swelled and faded? The golden record is one answer, created by a handful of people under a deadline. You might make different choices. That is the point. Thinking about what you would inscribe on a record for the universe is really thinking about what you value on this small world right now. Meanwhile, the Voyagers themselves just keep going. They have already left the heliosphere, crossing the invisible boundary where the solar wind gives way to the thin gas between the stars. Unless something collides with them, they will drift through the galaxy for billions of years. Long after Earth has been scorched by the red giant phase of our star, long after the last mountain has eroded and the last continent has sunk, those little machines will still exist. They will be extremely cold, completely dark, and utterly silent, but the records will still be bolted on. In that sense, parts of our solar system story have already escaped the solar system itself. None of this fixes the problems down here. Understanding the true scale of our solar system does not magically solve climate change or inequality or war, but it does shift the backdrop. When you remember that your daily frustrations unfold on a thin shell of air around a cooling ball of rock that circles a star in a galaxy that is just one among trillions, some arguments start to look different. Not smaller in the sense of unimportant, smaller in the sense of shared. Everyone you will ever meet lives on the same tiny stage. Every border we draw, every story we tell about us and them is being acted out on a dot. That is one of the quiet gifts of scale. It gives us permission to be both humbled and motivated at the same time, humbled because we are clearly not the center of the universe, motivated because this is the only universe we are ever going to experience. This one star, this one planetary system, this one window of time when the surface of this particular rock is stable enough, and warm enough and rich enough in liquid water for creatures like us to exist and ask questions. Nothing in physics guarantees that this kind of moment has to happen anywhere. Yet it happened here, so what do we do with it? One answer is the one we have already started. We build better telescopes and bolder missions. We return to the moon. We send humans to Mars, not as a stunt, but as the beginning of a long, slow expansion of life and mind across the solar system. We explore the subsurface oceans of Europa and Enceladus and Titan, not because we are guaranteed to find life, but because the question is too profound not to ask. We keep listening for faint radio whispers from other stars, and we keep sending our own whispers out. Not because we expect a reply, but because reaching out is part of who we are. Another answer is quieter. We treat Earth as if it were the rare and precarious oasis that all this physics suggests it is. We stop acting as if we can always move to another planet later if we ruin this one. We might someday build habitats in orbit or under the ice of distant moons, but for a very long time to come, the only place in the solar system that is naturally comfortable for human lungs and human hearts will be the one we are on now. Knowing the scale of everything else is not an excuse to give up on this world. It is a reminder that this world is unimaginably precious. The next time you see the star in your daytime sky, or a bright planet rising after sunset, pause for a moment and run the mental zoom you have built through this journey. Start from the street or balcony where you are standing. Pull back to the continent. Pull back to the whole planet hanging in space. Pull back until the orbits of the planets are thin lines and the star is just a bright point among many. Keep going until the entire solar system vanishes into the haze of the galactic disk. Then reverse the zoom and come all the way back home to a mind on a world that can hold all of that in a single thought. If that mental journey moves you even a little, then this documentary has done its job. You have not just learned a list of distances and diameters, you have absorbed a feeling for where you live and how outrageously unlikely it is that you get to be here at all. And if you want more long, deep, gentle dives into questions like this, remember to support the channels and creators who make them. A simple like, a comment, a subscription. These are tiny nudges that let projects like this keep going, the way small gravitational tugs slowly reshape an orbit. In the end, the true scale of our solar system is not just about emptiness and distance. It is about the thin, bright thread of meaning we weave through that emptiness by paying attention, by asking better questions, by sending fragile little machines into the dark and engraving records for strangers we will never meet, by looking up at the night sky and realizing that the most surprising thing in the universe is not the size of it, but the fact that for a brief moment, something in it woke up and wanted to understand.